to build this attractor, it's actually really simple in terms of it's just a single node that we're going to run some code on. So there's not a lot of complexity in terms of having to build lots of different things to make it work. We're really just going to create a single node and then just add a little bit of code to that, and that's going to basically enable us to kind of build up all the features we want. And so the first thing we're going to do here is go on the toolbox to entities at the top, and at the bottom we're going to click on node here. And what this is, and then we're going to click and drag in the space to create it, and then just right-click to exit draw mode. And what a node is just a simple object that has a transform, so it has a position and a rotation and a scale, and that's about it. And we can write some code on it. But the idea of a node is you can use it to kind of parent or child other objects to it, and by doing so, those objects will then, if it's a parent of children, those children will move with it, and so it allows us to organize things and kind of control things using a centralized position or rotation or scale to then control a bunch of other stuff. But for today, we're not even going to parent it, except maybe something at the end. We'll play around a little bit with that. But for now, we're just going to add some script directly to this node. And so how do we do that? So I have the node selected right now, and I'm going to go to the property editor here, and I'm going to select this onTick event here. And basically, when we do that, we get a little code window. So what is onTick? onTick is just some code that fires every frame. So every frame, this code is going to get called. And so right now, I'm going to write a little print statement here so we can kind of see it happening. So if I hit print ticking, when I hit play, you'll see that the console is getting kind of sent this message because every frame it's calling this ticking function. In fact, I can probably show a better example here. I'm just going to declare a little variable in here, f that equals 0, and then every frame I'm going to say f is equal to f plus 1, and then I'm just going to say ticking to string f. So basically what this is just going to do is compose a little message that's comprised of the word ticking, and then this is the concatenation. It's like basically merge two strings together. In this case, the string that's returned by this toString function, which converts our number here, f is just a number, to a string, which then can be kind of concatenated, added to this thing to create a final message. And so we're getting this value now that's increasing every frame. And there's one other trick that we can do here. If we say comma 1 here on this print statement, it merges it down to a single message here, and these will fade out in a second. So now we have a very simple way to see how this function works. Basically, every frame, this function is getting called, and basically, in this case, we're just adding a value. And so basically, the way to think about onTick is it's a great place to kind of perform any kind of behavior, any kind of thing where we want every frame some update to happen. And that's exactly where we're going to want to do our logic for our attractor. Basically, every frame we're going to kind of find all the physical objects in the space, and we're going to drag them toward us. Basically, we're going to attract them toward our node. But before we dig into those kind of details, one other thing that we kind of want to be aware of here, that one of the things we're going to be touching on today, is a variable type called a vector3. So I'm just going to store, I'm going to create a variable called the vector3 here, which is, all a vector3 is just an object that stores 3 numbers in it. So if you think of a simple number, n is equal to 1, let's say, that's essentially like a one-dimensional, like a vector 1, basically. It's just a single number is being stored in there. And then there's vector 2s, vector 3s, and vector 4s. So n is just basically a single value, whereas v is a value, here, in this case, it just happens to store 3 values inside it. And the reason why that's really important is that objects in 3D space are represented using 3-dimensional coordinates, i.e. 3 values. And so we basically just need a way of playing with those values in script, and we do that using these vector 3s. So for instance, this node object contains on itself a function called getWorldPosition. And what getWorldPosition does is it returns a vector 3. So now our v is the same as, in this case, vector 3, 1, 1, 1, except instead of, in this case, we're just storing this explicit value, 1, 1, 1. In this case, it's returning whatever its position is in space. So in this case, it's this value here, this transform position. And so actually, I'm just going to go ahead and print this. I'm going to say print to string v, so we can kind of see it. I'm going to give it its unique ID, so it only prints 1 on screen. And when I hit play, you can see that it's showing its current position. So as I move this node around, our variable that's getting returned by this getWorldPosition is we're storing in it this value, the current value of this node. And so we can see now what that value is, and we can play with it in script. So whatever we do to this value, we can then change it somehow and then re-inject it into the object using setWorldPosition on the self. And we're going to get into that as we build this attractor. So let's go ahead and start building the attractor. And I'm going to re-go over this as we're doing it, because there's a few other things we're going to be doing with these vectors, with these position vectors, to kind of figure out the direction of where things are and things like that. So I'll get into this more as we build this attractor. Okay, so the main idea of this attractor, as I was showing in the beginning here, is basically anything with a physics rigid body, anything that's physical in the space, is going to kind of get drawn to the node. So the first thing I'm going to do here is I'm just going to draw a bunch of objects, a bunch of boxes. So I'm going to go to Entities, click on Box, and then I'm just going to draw a bunch of objects around this node. And these are going to get attracted to our node. So I'm just going to create a bunch of objects. And so right now, obviously, if I hit play, nothing happens because we haven't written our logic yet. So I'm going to hit stop. So the first thing we need to do is we have to find those objects, right? We have to, in our script, we need to kind of find all the objects so that we can then apply these forces to. And so to do that, what I'm going to do is I'm going to declare a table. So this in Lua is just basically an array, but it's a little bit more powerful than an array because it can either be indexed using numbers, or you can use hashes. So you can use whatever, you can use a variety of different variable types to create a hash table. And I can explain this a little bit more in a future lesson. But for today, we're just going to be using it as a simple array. And then the next thing we want to do is gather all the objects in the space. So this might include these boxes, and it might include ourself. It might include all sorts of other objects we might have. And so we're going to have to filter it a little bit. But for now, let's just get all the objects. And so to do that, what I'm going to do is say self, which is our node itself, get space. And this is the space, right? This is the terrain space that we're here. When we click on the root terrain space here, this is the whole world. This is this whole space that we're looking at. So basically, self get space will get us up to that level. Will get us to the space level. Then we're going to say get child nodes, and we're going to store the result inside our table. And so now our table is going to be initialized with all the children of this space, all the objects of this space, which we'll now be able to. We're going to iterate through. We're going to step into each one of those elements. And then we're going to be able to say, okay, which only the ones we're interested in this case, the ones that have the rigid body, that have physical objects, physical properties, are we going to actually affect. So I'm now going to create an iteration. I'm going to iterate over these. I'm going to say for I is equal to 1 to the total number of elements in our table. So that's another really important thing to be aware of. This little pound sign here, this in front of a table type, which in this case is our table, will return the total number of elements inside it. And that's important. So that's going to basically say, starting at the first element to the number of elements, this for loop is just going to loop basically each time for every element inside this table, which is what we're going to need to be able to do to kind of access each element and do something to them. So let's actually, for fun, I'm just going to print out the name of every object that it's finding. So I'm going to just say print the node inside the table at index I. So again, this is basically saying of the table of all the items in the space, get me the item at I, which will be 1, 2, 3, all the way up to the table count. And then I'm just going to call get name. So get name is a function that lives on every object type, on every object that's returned by that's stored in this table, that will return the name. So when we hit play, it's showing us kind of a list of all the objects that are inside that table. So the default camera is the one we're looking through right now. So that was returned as part of the child nodes. The node itself here, this is our attractor node that lives in the center. It was returned. And then every single box entity that we drew. So now all of these things are stored in this table. So I'm going to hit stop now. Okay, so to make it a little bit simpler, I'm actually going to, so we don't have to constantly refer to this table object, I'm going to just say node is equal to table at I. So we're just basically, for every element here in this table, I'm just going to store it in a variable called node. It's a little bit easier. So this node will basically be equal to this, and then it's going to be this, and then this, and then this, and so forth. And the next thing I want to do is build a filter, basically. I want to basically say, okay, I want to see if this object has a rigid body, because things that have rigid bodies are things that are physical. So for instance, if I click on one of these boxes I created, when you create a box, by default it has a rigid body. And a rigid body means that it has these physics properties. So when I hit play here, it means that it behaves with physics. If I remove this rigid body, for instance, now it doesn't. It just stays wherever it happens to be. And we don't want to deal with those. We don't care about those. And so we're going to basically implement a little filter that will allow us to check for that. And we're going to do that just using an if statement. So I'm going to go ahead and add the rigid body back to this thing and hit stop. And so now what we're going to do is say RB, this is our rigid body, is equal to node get rigid body. So get rigid body is a function that every single one of these objects exposes that lets us access, it's this object here, this rigid body object on that object, and it will store it in this node, in this variable in this case called RB. You can call this whatever you want, but I just called it RB just to reflect that it's a rigid body. If this variable is empty, then we know the object doesn't have a rigid body. Else, if it has a rigid body, then we'll be able to kind of apply forces to it. So I'm just going to say if RB, then. So what this does, it says if this RB has something in it. This is actually equivalent to if it does not equal to nil, actually. So that's another way to write this. Basically, if this thing that's returned by this function, getRigidBody, if it's not nil, if it's not nothing, basically. If it's something, then it means we have a rigid body. We have an object that has one of these properties on it. And that's what we care about. We basically want to filter only the objects that have this attribute added to them. So as a shorthand, I prefer, instead of writing is not equal to nil, I just like writing if RB. That's just another way of saying that, basically. It's another way of asserting if it's non-nil or if it's true. If it was a variable that was true or false, if it was false, then this wouldn't happen. So if RB is basically another way of saying if it's something. But actually, for clarity, let's just equal to if it's not equal to nil. So this is the not equal sign, basically, in Lua. This is the equal sign. This would be only if it has no rigid body are we interested. But in this case, we're only interested in ones that have a rigid body, i.e. where RB is not equal to nothing, to nil. Okay, so once we get to this level, I'll go ahead and print again our node getName, and you'll see some of the things have been filtered out now. Notice that the default camera is now not in our list here, and the node itself, since this attractor node right now has no rigid body, it was filtered out as well. So there we go. So now we're dealing with only the objects with physical rigid bodies in the space. So okay, so now let's calculate a force, an impulse actually, that we're going to apply, a force that we're going to then apply via an impulse for each one of these objects. So now to do this, what we're going to do is what we're interested in is looking at the world position of each item. So like we did before, where we pulled out the world position, this returns the object's position. So that would be this position here, that would be this, wherever this center point of this box is over here, wherever the center point of this box is over here, and so forth. That's what getWorldPosition is going to return. So we're going to store that in a variable called the vNodePosition, vNodePos. That's just a variable name. You can make this whatever you want, but for this purpose, it's going to store the position of that object. And then we're also interested in the nodes, the attractor node positions. Actually, I'm going to rename this node here in the center to attractor node. That's a little bit better, so we can kind of identify it. So we also care about this thing's position, right? Because ultimately what we're going to do is we're going to calculate a force based on this thing's position and the position of every element in our space. And so our self position is equal to self getWorldPosition. So again, this self here just refers to the node itself, the context. We're inside this function that lives inside this node, which is the attractor node. So the self points to our self, basically. So we're basically saying, get me my own world position. And then in this case, it's get the position of the item that we're iterating over in this table, which is each individual one of these boxes. Okay, so once we have these two things, we can perform a little bit of arithmetic on these two vector 3s to calculate our vector, our delta vector. So I'm going to say v self-pos minus v node-pos, and then we're going to store this result in a new variable called vdiff. I'm going to just call it vdiff. And so I'm going to visualize this for you, what exactly we're doing. So I actually have in this space oh no I don't, actually I created a file new. Shoot, I had a vector here that I could use to visualize it. One second, I'm going to go ahead and recreate this. I'm just going to copy paste it. Pay no mind to this. I have a little scene set up where this is like to be able to visualize this. Very quickly, I'm going to recreate this tractor node, and then on tick, I'm just going to paste in the code we just wrote. So we're right back to where we started here. I'm going to create a bunch of boxes again, like such. And the reason why is I just had a little space pre-created that has a nice, nifty little arrow that I'm going to be able to use to show you guys what I mean by what the arithmetic here is actually doing. And so when I hit play here, there's this little object out here that I'm going to be able to use here to help visualize what we're actually getting here. Okay, so our node position in this case is going to represent each element's position as we're iterating through this table. And our self position is the position of our attractor node. And so what we've just calculated here, vdiff is equal to our self-pos minus our node-pos, is actually a vector that if I position this here So I'm going to set the starting point of that vector to be equal to the position of our attractor node. And then this is going to be the vector that's produced by each, as we're iterating over this table. That's what we're storing in this vdiff, basically. It's this here. It's this vector here. And so just think of it as a three-dimensional, all it is just three values. And those three values are basically storing the difference between this black position, this position here of this node, and the position here. So eventually we have three values that represent this line right here. But the problem is that this line, we kind of, what we want to do is really control the forces carefully. So we don't want to work with, I mean, I guess we could. We can directly work with this line in its current length. But a better way to work with this data is to normalize it. Because once we're normalized, we can then apply whatever numbers we want to that vector to then apply forces in a more controlled way, in an easier way. You can play around with it. I'll show you guys actually the difference between without normalization. But for now, what we're going to do on this vdiff is I'm going to call normalize on it. And what this specifically does is it will convert this vector here from a vector that has the length equal up until whatever the position of this object is. So it will stretch out to this. Once we call normalize, it will be normalized to only a unit vector. So that means its length is always 1. And that's really useful because it allows us to kind of remove that distance information. Like we get rid of the magnitude of the vector, basically, which is just the length to the object. And we have a nice normalized vector that we can then multiply other values to create forces. So if we multiply it, let's say, by a fixed number, it'll always be the same length no matter what. So we basically by normalizing it, we just get the direction information, but we squash out the magnitude. We reduce it down to a unit vector, what's referred to as a unit vector, that has exactly length of 1. So all of these, as we iterate and then normalize, will basically have an arrow that only points to the object, basically, with a length of 1, but that's it. And so that's basically what happens when we call normalize. So the other thing we want to do, and actually we'll need to do this before we call normalize, is I'm going to hit stop here, is we want to get the distance. So before we normalize it and we squash away that distance, we also want to get the distance, because actually that's going to be really useful for us to calculate forces. And this is where I'm doing this more for visualization standpoint, from a visualization standpoint, to kind of visualize the different aspects of a vector. But we can also not normalize it and get pretty much the same result. So the distance is going to equal to vdiff length. So before we normalize it, because once you normalize it, again, the length will become 1. Before we do it, we want to store the length of that vector. So the length of the vector between our attractor node and each individual item here, we want to store that in a variable. So this is just stored as a number. This turns into a number, basically, a simple one-dimensional number, which stores the distance. So it's whatever the length of this line is here, basically. So that'll be an easy way to basically scale our forces. So basically, the closer it gets, the stronger the forces are. And then the further away it gets, the weaker the forces are. And we'll be able to kind of modulate that using the distance. And then again, we're going to normalize this vdiff variable, so that internally our vector turns into just this. So now we have the distance value, which is a single dimensional value that stores the length of this vector, and we have a three-dimensional value that just stores the direction to each one of these things. So now we can finally calculate everything we need to calculate a force for this, and then apply it to each individual object. And so to do that, I'm going to basically create we're going to take our vdiff. This is our vector that's been normalized, and then I'm going to multiply that, and this is our v force, we'll say, by our distance. So we're back to the original vector. This is why by multiplying our normalized vector back by the distance, we're back to the original vector. So again, this is all a little bit being used to show an example here to kind of break down what a vector is. But we didn't technically need to normalize it. We could have just said, okay, vdist and remove the distance. But because we have the distance separated, we can do things like square the distance. That means that as it gets further and further out, it's going to get stronger and stronger the force, which is not what we want. We want to invert that. So 1 over the distance squared, for instance, is the inverse square of that. So that means it'll get weaker the further out it gets, which is what we want. We want the attractor to affect things closer to it, stronger than further away from it. And finally, what we need to do is actually apply this force to the object, to each individual rigid body. So in this case, RB is a rigid body, and we have this function here called apply a central impulse. And what this apply central impulse what it does basically is it takes in a vector, in this case our arrow that goes between these two objects, and it applies an impulse along that vector. And so I'm just going to pass in the v force. And let's see what happens. So we get everything's kind of collapsing to the center really fast. And there's a few reasons why this is happening. And we're going to kind of we're going to keep working on this until it gets more stable, basically. So basically we're applying forces. Now, the thing to be aware of is we're actually applying forces, since this function is getting called every frame, we're applying forces equals to whatever our frame rate is. So if our frame rate is 200 frames a second, we're going to apply 200 impulses per second. If our frame rate dropped to 10 frames a second, we would be only applying 10 impulses a second. So this isn't very robust. In fact, let's bring out the frame rate here. I'm going to go View, Show FPS here. You can see my frame rate in the bottom right-hand corner here. It's 230 right now. So when I hit play, basically, we're applying 230 impulses a second to each one of these objects. So that's no good. In fact, if I turn on VR, VR limits us to 90 frames a second. So I'm going to hit VR here so we can kind of see this and visualize this. And you'll see at the bottom right-hand corner that my frame rate now has been dropped to 90 frames a second. When I hit play, notice that everything's much slower now because we're only injecting 90 impulses per second and not the 200 of when we're out of VR mode. So we need to make this agnostic to the frame rate, basically. So I'm going to exit VR mode. We're back to our high frame rate here. And so how do we make this frame rate agnostic? So that no matter what our frame rate is, we're applying the same kind of proportionality. Our impulse is scaled accordingly. So to do this, what we're going to do is we're going to get the timeline that's kind of governing our space. So if you look at the train space, if I click on the ground here, it has a timeline in it. And actually, this is the default timeline that we see down here when I hit play. We need to kind of see how much time is elapsed between these tick events. And then that will allow us to kind of create a scalar, a value that we can scale our force by that's properly scaled by the frame rate, by our actual time that delays across frames. And so how do we do this? I'm going to say self get space. Now, again, this is just like we did before. Just like we're getting the child nodes of the space, we're at the space level. We can now query our timeline. So we're going to say get timeline. This is going to return this timeline object here. And then the timeline object has a function called get time elapsed from last tick. So that's going to return a time object that stores the total amount of time elapsed from last tick. So if your frame rate is 100 frames a second, it's going to be a value that's it's 100 milliseconds basically, versus if your frame rate is 10 milliseconds, it'll scale accordingly. So it's going to be a value that's going to scale with our frame rate basically. So I'm going to store that in a time value here. This is a variable that's going to store a time value that represents the time elapsed from the last tick. And by the way, how did I know about this function get time elapsed from last tick? Well, if you hit F1, let's say you have an object like the timeline, I can hit F1, and actually that'll bring up documentation here when you hit F1. And actually, I'm going to search for a timeline in here, this timeline object, and here it is, get time elapsed from last tick. I can click on that, get some information about it. So F1 is kind of your companion here. Make sure you hit F1 on anything. For instance, node. What kind of functions can I call on myself? I select node, hit F1, and here are all the functions, for instance. And that's just where we find get world position. It lives in here, for instance. And these are all the other types of functions that I can call on any node, for instance. And so definitely use F1. You definitely want to use this very often. In this case, timeline. We can see that get time elapsed from last tick is the function we care about here. Okay, so we're going to store that inside this tm variable. And so now we want to calculate a scalar, and we want to calculate a value that's going to scale based on the time. And so what we have to do for that, I'm just going to say our scalar, or well, we can call this like impulses per second, is equal to our time value. This is the time since the last frame. We're going to have to convert this to seconds because the time object itself just stores time in a kind of generalized way. We have to convert it to an actual number by calling 2 seconds. We could convert it, for instance, to hours, let's say, to get a value that's in hours instead. But we care about seconds. Seconds. And then how many impulses would we want per second? I don't know, 20 impulses per second is what we'd end up storing here. You can play with these variables, and we're going to have to kind of play with these numbers until it looks good. Okay, so now we're going to scale our force by this number. This means that now, regardless of our frame rate, we'll have a value that will scale with the frame rate. So hit play, And it's a very kind of, this equation here is making it so that it's not enough impulses. And actually, I find that this inverse square is not good. I mean, this is actually the proper way of representing gravity, and you'll definitely want to use this formula if you're trying to create, like, you know, a gravity situation where things accelerate, but but you can see what's happening is things, as they get near it, they kind of accelerate away really fast, and then all of a sudden they're far away and it's not having a lot of influence. And so what I find that works really well is just to get rid of these parentheses. By doing this, basically, we're basically saying 1 divided by the distance times the distance is a value that scales a little bit differently. And then we start getting something a little bit more interesting here when we do that. And so, again, if I turn on VR now, where the frame rate drops back down to 90 frames a second, you'll see that it will do the same thing each time I hit play. It looks identical because we're now factoring in the amount of time that's ticking between frames in our formula to determine what our force is going to be. So that's what we want. So that's kind of about it in regards to digesting down this thing. Again, the main things that we had to do here to build this is, number one, get those items that live in the space, find all those objects, iterate over those. And by the way, there's all, Lua as a language has all these statements like for and self, and there's a little cheat sheet that I refer to all the time because I don't always necessarily remember all the nuances of the language, and you can find it under the Learn menu. If you go Learn menu and go Scripting Cheat Sheet, I'm going to exit VR mode here so we can find it here. Learn, exit Scripting Cheat Sheet. It will open a documentation that lives on our support site that lists kind of all the different parts of the language. And so this is kind of a cheat sheet to quickly find all the different nuances of this language. It's not very long, but here, for instance, we can see the table, for instance, is just initialized using that. We saw the not equals sign is there. And there's a bunch of, for instance, how do you loop? Here are the different types of loops. So for I equals 1, this is what we use today. But there are other types of loops. You can also loop this way in a key value using this pairs function. There's also while loops and repeat, different ways of looping. So definitely refer to this cheat sheet to quickly figure out like what's like the syntax for statements and all that stuff. It's super useful. So again, reviewing what we did here, let's not worry about this time thing yet. We'll come back to that. So the first thing we were doing here is we initialize this array, this table. We then use this get child nodes on our space to kind of fill that table with all the objects in the space, but that also includes the camera and a bunch of other stuff which we don't want. So then as we're iterating over, we're specifically querying each item's rigid body. The camera doesn't have a rigid body, and neither does this node here in the center. So that by doing this if statement here, it's basically testing to see if this is even something. If it returns nothing, this function, then we know we're not dealing with a physical object. So we're filtering just for objects that are physical, and then we're calculating a force based on the relative position of the object and our attractor node. We're normalizing that. I mean, again, this just allows us to work with just a direction. So actually, we're pulling out the length of our normal, the normal that's of the vector that's formed between our attractor and our object. We're getting the length of that. It's stored in a simple number, and then we're normalizing that vector, so it squishes it down to just simply being a unit vector. So in other words, it's within a sphere's within a radius of 1, basically. So we just have a direction, basically, that's normalized, and then we can kind of scale that back out based on, again, in this case, this not quite inverse square kind of situation, and then applying that impulse to the rigid body, to each individual object's rigid body. So that, in fact, if we hit F1 and apply central impulse, it brings us to the documentation for it. I'm going to click on rigid body here. Here are all the functions you can call on an object's rigid body, including applying torque impulses, and you can create constraints, and you can. The other big one is setting and getting the linear and angular velocity. That's really useful to see what direction it's moving and what is its speed and things like that. So that's what we did. And then the last thing we had to do is, because onTick is called at every frame, some people's frame rates might be higher, some people's might be lower. We need to scale our forces based on our time, the actual time elapsed across frames. And that's what we did here. We got the time elapsed from last tick using the timeline that we pulled out of the space. And then we kind of said, okay, how many impulses do I want to inject a second? 20 per second, basically. So it's scaling this force such that apply center impulse will be acting as if it's, every time we call it, it's 1/20th in a second, basically. And that's it. And we get this kind of cool behavior. And so the cool thing is, now that we're done, we can go ahead and close this scripting window. And by the way, the script for this is already, it lives, we've just broken down this attractor object that you can find under physics here. So if you click, you can actually create it, and it's already pre-written for us. So we've just broken down something that's already actually in here that lives under physics. So now when we hit play, we have this kind of cool, this kind of interesting thing that we can kind of play around with. If I grab that attractor node, I can kind of move it around, and the things kind of move with it. And the other cool thing we can do is, again, we can parent this attractor node to an object in the space. So for instance, if I have a car, or if I have, so I go under actors here, I'm going to create a vehicle, and I'm just going to parent, and actually the vehicle is going to be attracted as well, but it's much heavier. And oh yeah, that's actually another thing that we'll actually do here. So right now, the way the attractor is set up, let me keep the car out of this for a second. If I have a really, really big object, by default, when you draw an object, it pre-initializes its mass to kind of be proportional to its size. It kind of assumes a density for the object, and based on its volume, it calculates the mass. So the bigger object now is not going to get attracted because it's too heavy, it's too massive. So one thing we can do is we can modify our script to kind of scale the force based on the object's mass. If we do this, no matter how big the object or no matter how massive the object is, it will get attracted to this attractor. And so to do that, we're just going to simply multiply our force by a rigid body's mass. So that's basically just multiplying it by this value here, this mass value here. So now, no matter how big or small the object is, and in this case, friction is kind of preventing this box from moving. But if I make a giant sphere here, now you'll see that the sphere will be attracted to this. Without that, if I go back and remove that mass, you'll see that the sphere won't move because the sphere is just too massive to get pulled toward it, unless I knock down its mass. So I'm going to multiply this by the rigid body's mass. So again, the rigid body RB value here is just this variable that stores the rigid body, and I just pull out its mass here. And that means everything, including big, massive objects, will be attracted to this. So not necessarily a very realistic attractor in that regard, but it is satisfying from a standpoint of now we can kind of do all sorts of fun things with it. So in this case, I wanted to take this thing and stick it on our car here. So I'm going to just take it, I'm going to stick it kind of near the car here, maybe behind it, or we'll put it in the center. And I'm just going to drag and drop this attractor node onto the vehicle, and now when I hit play, as I drive this car around, we're kind of inundated with these objects that are trying to attract to it. No matter where we go, they'll chase it. It's kind of already fun, right? You can kind of almost think of a game here. Now, if maybe we create a giant, like a wall here, a protection wall here, that I'm going to set this as fixed. It's rigid body. I'm going to make it not movable. So now, maybe the car can get some, like, if it like manages to get just the correct way around this wall, I can kind of prevent these things from getting it. Well, you get the idea. I'm just going to pick up and move it directly here. So our other objects are behind this wall here. So parenting this is really fun. Another thing we can do, I'm going to put this back in the space, delete the car, is we can create multiple attractors. I'm going to hold down Alt and make a copy of it, and now we have two. And so they kind of go into the center of this space, which is kind of interesting. I'm going to create an emitter, a node emitter, for instance, and then this is going to emit nodes, and now they're going to kind of go kind of in the center of these two. I'm going to crank up the number of nodes that are going to be emitted here. I'm going to click on the node emitter, expand continuous. It has this pulse here. I'm going to expand this pulse and just increase its frequency. So now it's going to emit a lot more. So you can kind of see that they're kind of taking a path that's kind of between these two, which is kind of interesting. And then the other thing I can do is maybe crank up the total number of things that it can live. Max simultaneous here is the total number of items that can kind of be emitted by this emitter before they're removed. So you can kind of get these interesting things. So two attractors do this. If I create a third attractor, it does some other kind of interesting stuff here. And then you can just pick up and move these things. So in VR, this is interesting because what we can kind of do is stick these things on hands, for instance. You can kind of stick it on hands. So I'm going to delete these other attractors here. I'm going to create a VR rig very quickly here to show you guys that. VR rig preset. I'm going to plop this in the space. And then I'm going to just child this node to one of my hands, let's say. And you can kind of do this already with some of the interactions and tools already built in, but I'm just going to kind of break this down here so you can see it. So on my left hand, I'm just going to drag and drop this onto the left hand itself. When we do that, it's still going to maintain its position wherever it was in space. So as I move my hand, it'll have this weird offset. So I'm just going to click on the attractor node that we just dragged onto the hand. I'm going to view its transform information. I'm just going to set these to 0. When we do this, it's now at the 0 location of the hand, basically. So now it'll move my hand and it's offset at 0. Maybe we'll offset it slightly in front of the hand so it'll kind of attract to that. So now, if we go into VR mode, and hit play and present this, you'll see that these things are now attracted to my hand. So at my left hand, so I'm going to grab my left hand here, and you can't see because they're kind of like right in front here, but as I move my hand here around, you can kind of see that they're all kind of being chased. You can very quickly imagine all the things you can kind of do with that. You could place this somewhere in this. You can make it offset really far away from your hand, or maybe another thing you could do, for instance, is what if we want a button that when we press that button, I'm going to move this attractor back into the parent space here, so that we can kind of move it somewhere into the middle space. Let's look at another interesting case here. How about we create a button that when we press, it turns on the attractor, and then we can turn it on and off. So another thing to think about, I'm going to go back into the object script of the attractor, is right now this is going to get called every frame. And you'll notice that all nodes have this active state. If we set this to false, you might think, oh, okay, now onTick is not getting called. That's actually not the case. It's still going to get called every frame. And so you'll see when I hit play, even though this is inactive, it's still calling onTick every frame. And there's certain reasons for that, but basically we'll have to implement our own little logic to ensure that doesn't happen. And all we have to do for that is just to simply say if self dot active, if not self dot active, then return. So now it's going to look at its own property, its own active property, and if it's not active, then it's just going to return. It's not going to call the rest of this code. And so when we hit play, now it's active, and now if I deactivate it, it's turned off. And so now we can just programmatically set the active state of this, and then we can have a cool kind of way of turning something on and off. So for instance, one way of doing things programmatically is to use triggers. We looked at this in the first demo, in the first lesson. When something passes through this, we can have some code get called. I'm going to just double click on the trigger. When something enters it, I'm going to then select the attractor node. I'm going to undock its properties. I'm going to just drag and drop this into here. It creates a variable that stores our attractor node object, and I'm just going to set its active state to true. So when something passes through this, it's going to activate this, which will activate this trigger. So now imagine I have like a car, or like a little game here. So I'm going to create an actor, a roll, a movable ball. So this movable ball, kind of goes on. I'm controlling it right now with my keyboard. Now it's going to go through this, and whoop, and now the attractor's enabled, and myself and all this other stuff are attracted to kind of the center of this. So already you can kind of imagine these kind of interesting cases. What if we, another thing we could do is, let's make the exit of this disable the attractor, for instance. So on exit, let's have it actually disable the attractor. I'm just going to copy and paste this code and set active to false. So when something exits this, it's going to disable the attractor. So now what if I place this in the middle of this where these attractors are? Some things will pass through it and enable it, and some things will pass out of it and will disable it. And see what happens when we do this. So now it's enabled. Now some things are passing through it, now it's disabled. Now as soon as something re-enables, goes through it, it reactivates. So you have this kind of interesting, in this case, yeah, we don't really have, maybe what we can do is point this toward it. So now it's going to activate and then periodically deactivate. I'm going to reduce the rate at which this emits at. So it emits at a much slower rate here, and then it's activating, kind of deactivating. Maybe not the best example. A better example here is to create a button that we can push that will turn it on and off. So let's do that really quickly. I'm just going to create let's create a rounded cylinder. This will represent our button here, and we'll give it a different color. And we'll also want to make sure it doesn't have a rigid body. Actually, we'll let it have a rigid body because it'll get attracted now, but that'll be kind of hilarious. So I'm going to select this button here. I'm going to click this tiny little button up here next to the rounded cylinder. When we click on this and undock it, this is called the menu button. And then I'm going to add interactable on this. And then this, when we click on this interactable object that's added, it adds these additional events that we can implement. And on press is what we care about. When we press it, we want to turn on our, actually let's do on hover. When we hover our mouse on it or hover our laser on it, it'll turn on the attractor. When we hover off of it, it will turn it off. So I'm going to click on hover on, and I'm going to select the attractor here. I'm just going to drag and drop this in here. And so when we hover on it, it's going to set active to true. And when we hover off of it, and we can actually just type in on hover off here. I'm just going to just type it in directly, or you can click on it up here, but this will also do it. It will turn it off. So now when I move the mouse over this, it attracts, and when I move the mouse off of it, it stops. So this is kind of interesting. And this will apply to the lasers too in the space. If I go into VR mode, hit VR, and now when I move this on top of this, you'll see that it'll attract, and then when I move off of it, it will stop. So kind of an interesting dynamic here. So the attractors is a pretty fun one to play with. It's additive. You know, you can create multiple ones and get lots of interesting effects, and you can very quickly kind of start to play with it and do some really interesting things. So like, and I'm just going to leave you guys with just a final set of things here. We could do, like, for instance, on this viewport here, I'm going to add an image filter, for instance, and maybe we'll do like a sketchy image filter, and so it's kind of interesting visually. And then maybe we'll build out the terrain a little bit here in the background. Kind of create this interesting mountain here. Maybe we'll actually move this attractor up the mountain, so the objects have to drag themselves up the mountain here. So now, as we move here, as long as I keep hovering over this thing here, they kind of go up the mountain, which is kind of cool. Actually, let me make this thing fixed. So I'm just going to make this thing a fixed button in space. So I'm going to set its rigid body movable to false. Now it doesn't get attracted. I move over it. Oh, and right, I did that in playtime, so it reset everything. That's another thing to be aware of. If I hit play and I move something, as soon as I hit stop it's going to reset its position. So if you want to commit its position wherever it happens to be, and you've moved it at playtime, just remember to hit Control T, select it and hit Control T. Then it will commit its position. When I hit stop, it remains up there. So here we go. I'm going to hit play. I'm going to move the mouse over it, and things are going to get attracted to the top of this mountain here. Kind of interesting. So that wraps up this tutorial. Thanks for watching. Any other questions, please hit the Discord channel. I'll be there answering questions, and we'll take requests too, and we can modify this example, or we can try something else. Please shout away, and we're happy to show you guys anything you guys want to see. Thanks.